Let's now look at an example of projectile motion with an angled launch. Let's read the problem. A football is, oh, bad spelling there, we'll live with it. A football is kicked at an angle of 37 degrees with a velocity of 20 meters per second. Calculate A, the maximum height, B, the time of travel before the football hits the ground, C, how far away it hits ground, D, the velocity vector at the maximum height, and E, the acceleration vector at the maximum height. Assume the ball leaves from the ground. Alright, I've gone ahead and drawn a picture of what's going on over here. The first thing you have to do in any time you have an angled launch like this is we have to find the components of the initial velocity vector. So I'm going to draw it off here, I'm going to duplicate it off to the side, and we will go ahead and calculate those. If V0 is 20 meters per second, VOX, the X component, the one that would look like that, is going to be V0 times the cosine of the angle. So that's 20 meters per second times the cosine of 37 degrees, which is going to come out to 16 meters per second. V0y, which would be the one that looks something like that, is 20 meters per second, but this time times the sine of 37. And that is going to be 12 meters per second. In this type of problem, once you find these components, forget that you ever knew the initial velocity. Now there will be problems where you solve for that, but in most cases you'll be given that and you'll have to find the components. These components are the only things that should show up in your equations. Never, ever, ever this once you find this. Word to the wise, I've seen it happen a million times over the years, and I don't want you to be victims of what I always see happen. So now that we found that, let's look at, first of all, what we're trying to find here, the maximum height. So we want to know delta y when it's right there at the top. The height is the vertical displacement. We start at the bottom and we want to be up here. Now, this actually isn't very hard. This is just like when we threw a ball up in the air. When we wanted to know how high it was at the top, we set the velocity, the final velocity, equal to 0. We're going to do the same thing here, except for if you were to, let's draw in that velocity vector when it's up there. I know it's a little crooked, but I'm going to live with it. When I'm up here, my v final y, my v final x is equal to whatever this is over here, because remember, the x component of the velocity never changes. So that is 16 meters per second. Now, is that going to be as important to us as v final y? Nope. But just have to point that out, that at this point it's moving horizontally, so its motion is all horizontal, and the y component of that is 0 because it's a horizontal vector, which means that if we know that v final y is 0, we're looking for delta y, we know what v initial y is, we should be able to do exactly what we did many times before. And so I'm going to do that right over here, which is we're going to pick an equation that works well in this circumstances, which is this guy. I almost sometimes want to call this the max height equation because it's usually the easiest way to find the max height. What we've got is this equation, and we know already that this is 0. So if I solve this for delta y, I'm going to get negative VOY squared over 2g. And if I plug the numbers in, that's negative 12 meters per second squared over 2 times negative 9.8 meters per second squared. And that is going to come out to 7.35 meters. There you go. Exactly the same as when we just did straight up and down motion. Now what about part B? For part B, we're looking for the time of travel before the football hits the ground. Now, if I start at the ground and I end up at the ground, this again should look kind of familiar from when we did our free fall stuff. If I start at the ground and end at the ground, my total delta y displacement is 0. Coupling that with the initial y velocity that we already have, and g, we can find t using the equation that looks like this. Delta y is 0, which means if I divide both sides by t. 0 divided by t is 0. And I divide each of these terms by t. I'm going to wind up with t equals -2 VOY over g, which is -2 times 12 meters per second over -9.8 meters per second squared. And that gives me a time of 2.45 seconds. All right, we're on a roll. Now let's see what's next. How far away it hits the ground. Okay, so what we're talking about when we say how far away it hits the ground is delta x. This is also known as the range, total distance it traveled. And again, one of the things we love about this is there's only one equation that you use in the horizontal direction, and it's delta x equals VOX times t. We have both of those things, so let's just plug them in. It's 16 meters per second, and we were in the air for 2.45 seconds. That is going to give us a range of 39.2 meters. So once you get past the first step, we accumulate more information, it actually starts to get easier. All right, how about D? Well, we kind of already discussed D when we were doing part A. And it says, what is the velocity vector at maximum height? Well, we described it. It's pointing to the right. It's all horizontal, no vertical. And it's got to be equal to the initial x velocity because that never changes. So this is very easy. The v final at that point is 16 meters per second to the right. Part E is kind of just a conceptual question. The acceleration vector at maximum height. The acceleration vector, A, is always -9.8 meters per second squared. Actually, we should be more formal with this since they're asking us to get, we're going to say 9.8 meters per second squared down. We know that that's negative when we're talking about the vertical axis, but we're just going to do it that way to be cool. So this is just one example of many angle launch problems you can wind up doing, but you get the idea. Most important thing, get those components down of that initial velocity before you do anything.